Hello everyone, thanks for coming. Today we're going to do a review of our week 11th lecture for the ODE course. In this week, we talked about homogeneous constant coefficient first order ODE systems. So that is to say, we talked about the system x dot equals to ax, where a, this matrix, is constant coefficient, is constant. The coefficients do not depend on the time variable t. So a specific case is the case when A is a real and symmetric matrix, which is also called a Hermitian matrix. So in this case, all eigenvalues of A are real, and even with repeated eigenvalues, there exists a full set of n linearly independent eigenvectors. Therefore, the general solution for the system x dot equals to ax can be expressed as x as a linear combination of psi erit, where psi is the eigenvector corresponding to the eigenvalue ri. If eigenvalues occur in complex conjugate pairs, that is to say, if A is not real symmetric and if we have complex conjugate pairs of eigenvalues, then there may still be n linearly independent solutions, and we can always form two real value solutions from a complex solution. So what if the matrix A has repeated eigenvalues? In that case, the number of independent eigenvectors may be smaller than the algebraic multiplicity. Additional solutions of the form TK psi may be required to construct a fundamental set of solutions. Finally, if the coefficient matrix A is complex valued, then the complex eigenvalues need not occur in conjugate pairs. The eigenvectors are generally complex valued even if the eigenvalues are real. Therefore, the solutions may be complex valued and we may not be able to get real value solutions. So what if the matrix A is real valued but it has complex valued roots? So in this case, if A is real, the complex eigenvalues always occur in conjugate pairs, lambda plus I mu and lambda minus I mu. Therefore, we can get real valued solutions from complex eigenvectors by separating the real parts and the complex parts. Let's suppose the eigenvector psi equals to A plus IB, then we can write the solution xt as in the form of real part plus complex part. Because the matrix A is real valued, we know that the real part and the complex part by themselves must solve the ODE respectively. Therefore, we can generate two linearly independent real solutions from this complex value solution. So what if A has two complex eigenvalues and remaining eigenvalues are real and distinct? In this case, we can get the general solution in this form, C1 ut plus C2 vt, where u and v are real and imaginary parts of the complex mode solution, and the rest are the real eigenvalues and corresponding eigenvectors. Specifically, for a 2x2 real system, two-dimensional ODE, if you want to classify the equilibrium, then we need to think about different cases. Real eigenvalues of opposite size means that the equilibrium is a saddle point. Real values of same size and unequal means that the equilibrium is a node, which means it can be either stable or unstable depending on the signs of the eigenvalues. Finally, if the eigenvalues are complex with non-zero real parts, then the equilibrium is a spiral point. In this thing, if the real part is negative and source if the real part is positive. The eigenvalue analysis for the coefficient matrix A determines the qualitative behavior of trajectories for the 2x2 system. real and complex eigenvalues lead to distinct solution structures and very different phase plan geometries. Finally, we talked about the fundamental matrix method. So the fundamental matrix is to combine the fundamental solutions together to form a n by n matrix. Because the n vectors, they form a fundamental set of solutions, the determinant of this fundamental matrix is always non-zero. If we can get the fundamental matrix, we can write the solution to the homogeneous differential equation x prime equals to ptx as xt equals to fundamental matrix times the inverse of the fundamental matrix at t0 times the initial condition x0. Specifically, if the fundamental matrix at t0 is identity matrix, then the solution can be simply written as xt equals to phi t x0. Specifically, if pt does not depend on time, we have x prime equals to ax, then the solution can be simply written as xt equals to eat x0, where eat, this is a matrix defined by using the Taylor series. If the coefficient matrix A has n linearly independent eigenvectors, then it can be diagonalized A equals to t d t inverse with the diagonal matrix D. Therefore, the general solution can be written as xt equals to t e dt t inverse x0, where the matrix e dt is also a diagonal matrix. Thanks for listening.